Okay, can everyone see it?
Yes, we see it perfectly.
Yeah, good. Okay, thank you so much. Yes, I'm a PhD student at the University of Copenhagen. And the work I will be talking to you about today is about with my supervisors, Radek Wojtek and Adriano Agnello. Just to let you know, I made my slides so that you should be able to put the Zoom window in the left upper corner if you want, so it shouldn't obscure the text. So the title of our work is Cosmic Dissonance, because there's a tension between the early and the late universe, which might point in the direction of new physics. So let's go back to when it all started, when Edwin Hubble was looking at galaxies around him, and he measured the distance to the galaxies and how fast they were moving with respect to us. And he discovered that galaxies that were further away were also moving away from us faster. So this led to the groundbreaking discovery that the universe is expanding. And he also calculated this present-day expansion rate, so the Hubble constant, as it was named after him, and he came up with a value of around 500 kilometers per second per megaparsec. Now we know that was pretty far off, and actually it's closer to a value of 70. And then we also discovered another way of measuring this present-day expansion rate, which is looking at the first light of the universe, the cosmic microwave background radiation. By looking at the peaks in its power spectrum, you can also get a measurement for this present-day expansion rate, which also gave a value of around 70. So we seem to be pretty much on the right track of understanding our universe. But then precision cosmology came along. And now we know that the CMB actually measures a value of 67.4, while local measurements give a value of 74.0. This is from supernovae and Cepheids. So this difference between the two measurements of the Hubble constant is actually a big problem in cosmology. And it's also known as the Hubble tension. So of course, it might be true that some systematics or hidden mistakes in one of the measurements is causing this, but it also questions our understanding of the universe, because the CMB-based method has to use a cosmological model in order to carry out the measurement. So they use the best standard model that we have, which is the lambda CDM model. But if something turns out to be wrong with lambda CDM, then this might explain why it gives us a different outcome for the Hubble constant. So in this talk, we'll first see how we can determine the Hubble constant and the sound horizon from local data sets. And then we'll also explore some extensions to lambda CDM, so some new physics, to see if this can resolve the tension. But first, let's take a step back, because even though this problem is always referred to as the Hubble tension, it's not just about the Hubble constant. There's also another cosmological parameter, which is really important and doesn't really get all the attention it deserves.
Nikki, excuse me. Are you changing the slide? We just see the first slide of your presentation.
Oh, really?
Yes.
Oh, I've been changing them a lot. Okay, that's strange. Okay, let me try to share it in a different way. Do you see it changing now?
Yes.
Yeah.
Nice.
Oh, okay. Okay, that's a shame. Well, very brief recap. Edwin Hubble, he discovered that the universe is expanding, and his first guess was pretty far off. So then with two different methods, local measurements and methods based on the cosmic microwave background radiation, you could both measure the expansion rate of the universe, and this gives you a value of around 70. But nowadays, the measurements are so precise that the CMB actually gives a value of 67.4, while the local ones give a 74.0. So this difference between the two is a very big problem, which is referred to as the Hubble tension. Okay, so yes, first we are actually looking at a different parameter that also plays a very important role in this problem, which is the sound horizon. And this parameter is very intimately linked with the Hubble constant And it's also key in determining if some of these proposed extensions to the standard model work or not. So if we go back to the very early universe, before the CMB, before recombination, all the baryons were ionized and they trapped the photons in this baryon photon plasma. So if you would have an overdensity in this early universe, then of course matter would be attracted to it gravitationally, but also because of this photon pressure, there would be a pressure exerted outwards. And these counteracting forces of gravity and pressure resulted in oscillations, very similar to sound waves. So these waves continued to travel out in the early universe. And if two waves would meet each other, then they would compress and form a region of a higher density. And this continued to evolve in this way until the universe cooled down enough to become transparent for radiation. And then the photons and the baryons decoupled, so the pressure fell away. And at this moment, the patterns that were created were frozen in place. So the radius of the sound horizon at this time, at recombination, is referred to as the sound horizon. And we can actually observe this also in galaxies around us. If we look at very large galaxy surveys, then we can see that it clusters in a certain way. And this is, of course, a very exaggerated image. But if we look statistically at the data, then you can also obtain the scale of the sound horizon. And this is called the baryon acoustic oscillations, or BAO. So by comparing the sound horizon at recombination to the sound horizon at different redshifts, we can learn a lot about the expansion of the universe. Because if this is a signature that we measure in galaxies around us, then this signature can either be explained by a short sound horizon in combination with a high expansion rate, so a high Hubble constant, or a high sound horizon in combination with a low expansion rate. So in this way, these baryon acoustic oscillations constrain the product of the Hubble constant and the sound horizon. And this means that they're also very degenerate with each other. So knowing one, you will also know the other. And here we can see a plot of the Hubble constant and the sound horizon. And this yellow banana shape is everything that the baryon acoustic oscillations constrain. And it's very useful to visualize the Hubble tension in this way, because if you look at the CMB measurements, for example, carried out by Planck, they measure a high sound horizon and therefore a low Hubble constant, while the local measurements measure a low sound horizon and a high Hubble constant. So in this way, it's really not just a tension in the Hubble constant, but a combined tension. So now that we know a little bit more about these important parameters, let's have a quick look at how they can be determined using local data. And this local determination of the Hubble constant and sound horizon, it's kind of similar to how Edwin Hubble did it all these years ago. But then, of course, now we're able to see much further into the universe. So our data points are extending much further out. And you can also see that because of that, it's not a linear relation anymore, but it's actually a bit more tricky to fit through all the data points. And we know one way that we can fit through these data points really, really well, which is using our standard lambda CDM model. But even if you're a bit skeptical of this model and you don't trust it, or if you just want to make minimal assumptions, you don't have to use it. There's also other ways. For example, you can do a Taylor expansion, where you can introduce more terms to make it more flexible. And there are also some very promising machine learning methods that can also fit through the data and get the shape of the expansion history of the universe. So in this way, the local determination of the Hubble constant and sound horizon can be done in a way that does not depend on the cosmology. It does depend, of course, on the data sets that you use. This is very important. So I'll just share with you an overview of the ones that we use for our research. So for relative distances, we used supernovae and baryon acoustic oscillations. And these are really good in mapping out the shape of the expansion history, but they don't give you absolute distances. So you still need to calibrate them with something else. And for this, you can use different measurements. So very nearby, you can use Cepheids, as carried out by the SHOES team, or the tip of the red giant branch, as carried out by the Carnegie-Chicago Hubble program. And then if you go to higher redshifts, you can also use gravitationally lensed quasars. So the Holy Cow collaboration have determined very accurate distances to those. And this is useful because the other data points are also at a bit higher redshifts. So you would like to be able to calibrate them also at high redshifts. So combining these data sets, the result that we get, this is if we combine supernovae and BAO, and if we only calibrate it with the lensed quasars, holy cow. And then we can improve, we can shrink the contours a bit if we combine it with a calibration by Cepheids or the tip of the red giant branch. You can see the results here. And it's actually interesting that these don't really agree with each other either. So there's also a little bit of tension here. And then comparing these local measurements with the value that we get from the CMB, from Planck, which is over here. So it doesn't agree with the local measurements. And actually, if you compare it to the lensed quasars and the Cepheids, then there's a 5 sigma tension between it. So we're really starting to take this problem very seriously. And just to remind you that these local contours, they can be carried out in a way that does not depend on the cosmology. While the CMB-based ones, they have to use a cosmological model. So they use our standard lambda CDM model. And now, of course, there's been a lot of speculations that maybe if we can change something about lambda CDM, we can make these contours shift closer to the ones of the local data points, and therefore reconcile this Hubble tension. So this is what we looked into. We investigated 4 extensions of lambda CDM, but actually it turns out that most of the ones that are offered can be divided into 2 different categories. So you can either change the early physics, so before recombination, before the CMB, or you can change the late physics after recombination. And in this way, how the Hubble constant is derived from the CMB is you can measure the angular size of the sound horizon, which corresponds to the size of these fluctuations, the dots in the CMB. And then you can get the physical size from the physics of the early universe. And then combining this physical size measurement with the angular size can give you a distance from us to the CMB, an angular diameter distance. And then if you use the lambda CDM model, you can convert this distance into a measurement of the Hubble constant. So this is how the CMB is always used. And in this first model, what they changed is you can add some sort of exotic component in the early universe before the CMB. And this can be, for example, early dark energy or extra relativistic particles, some sort of radiation. And this will change the properties of the early universe and in turn give you a shorter sound horizon. Now we still measure the same size of the fluctuations, so the same angular size, but a shorter physical size. So this means that we will infer a shorter distance from us to the CMB. And shorter distances corresponds to a higher expansion rate, which is a higher Hubble constant. So this is the goal. And then for the second approach, they don't change anything before recombination, but after the CMB, they can introduce a phase of accelerated expansion. So these white lines, they correspond to the space expanding according to the standard lambda CDM model. And in these alternative models, there is an extra accelerated expansion. So we measure a higher Hubble constant as well. And some examples of models that do this are WCDM or PED. So when we compare these 2 approaches, we see that the first one changes both the sound horizon and the Hubble constant, but the second one doesn't change the sound horizon, only the Hubble constant. And as we'll see now, this is also why these models do not work. So going back to the results and the comparison, and now if we introduce the changes to the early physics, then the contours look like this. So you see that they shift closer to the local measurement. So it solves the tension a little bit, but it's not really enough. And then for the changes to the late physics, here, because you cannot change the value of the sound horizon anymore, the contours can only move to the right and not downwards. And then you see that this is really not a solution for the tension. Actually, it can make it even worse because you move away from this orientation and you also don't satisfy the BAO measurements anymore. And lots of models have been proposed that are supposed to solve this Hubble tension, but actually they don't really solve it at all. So I really want to emphasize that the tension is a problem in both parameters. And if you have a model, then you should really do a joint inference on the sound horizon and the Hubble constant to see if it works or not. So concluding, there's a tension between local and CMB-based measurements of two fundamental cosmological parameters, the Hubble constant and the sound horizon. Now we can carry out the local measurements without assuming a cosmological model. However, the measurements based on the CMB require a cosmological model. So they use the standard lambda CDM one. And some speculations about new physics have been made, whether this can resolve the tension. And if this new physics is in the form of extensions to lambda CDM, then it can follow two strategies. They either change the early physics before recombination, which will slightly decrease the tension, but not really enough, or they change the late physics by adding some late form of extra dark energy and accelerated expansion. But this can only change the Hubble constant and not the sound horizon, so does therefore not offer a solution to the problem. Now, coming back to these early extensions, changes in the early physics, we might actually be able quite soon to say whether some of these are true or not, because these early extensions, they introduce very distinct signatures in the small scales of the CMB. And the only reason why there is some room for speculations now at all is that these small scales are not really well constrained by Planck. But with future CMB measurements, such as the Atacama Cosmology Telescope and the South Pole Telescope, they will be much better at constraining the small scales. So hopefully we will soon be able to either prove or disprove some of these extensions. And finally, I think it's also very important to take a hard look at any systematics in the local data, because lately there's been an interesting new result where they used gravitationally lensed quasars, but then they combined it with a bigger data set, and they also relaxed some of the assumptions they had on the model. And this gave them a value of 67.4 for the Hubble constant, which is exactly the value from the CMB. But of course, these uncertainties are quite big, but it's still very interesting. And here as well, there will be lots of future missions coming in that will bring new data and hopefully shed some light on this situation. So I'm very curious where this tension between the early and the late universe will lead us. Thank you.